This is section 1.7, number 3. We are given the following differential equation. dy dt is equal to y squared minus ay plus 1. And we're going to refer to this as our function of y that depends upon the parameter a. We seek equilibrium values. Equilibrium values when f sub a of y is 0, but it's just a quadratic, and so we find values that the values of y that will make this true are a plus or minus the square root of a squared minus 4 all over 2. Well, the radicand, the expression under the square root, will be negative if a is in this region. So if a is a number smaller than 2 or bigger than minus 2, there'll be no real roots. No real roots. So no equilibrium values. Okay. If so that's one case. Let's just make some cases here. If a, I want to stay in black. If a equals 2 or a equals minus 2, there's exactly one equilibrium value. Namely, y is equal to a over 2. If a is, one second, stay in black here. If a is bigger than 2 or a is less than minus 2, there will be 2 equilibrium values. Equilibrium values. And we'll take a look at these two graphs. And you should use a calculator and check that that when a is bigger than 2, let me just double check myself. Right, when a is bigger than 2, we have pictures that will look like this. Our 2 roots will be here and here. And when a is less than 2, our pictures will look like this. Okay. And our roots will both be negative. And in both cases, our 2 roots, I'll call them y1 and y2. y1 and y2, they're both given by y1 is going to just be a over 2 minus square root of a squared over 4 minus 1, and y2 will be a over 2 plus the square root of a squared over 4 minus 1. A equilibrium value y1, this equilibrium value y1 will always be a sink because the slopes here are negative in both cases. Sink here, sink here. Equilibrium value y2 will be a source because the slopes here are positive in both cases. It's going to be a source. And so when we make phase lines, I will start with the range where a is less than 2 and bigger than minus 2. There are no equilibrium values. The function is always positive with those values of a, and so our phase line looks like this. When we reach the value of a equal to 2, we introduce one single node, equilibrium value. And if I were to look at the graph of such a function, I would see that I'm increasing. I have positive slopes in both cases, and it looks like this. And when I'm bigger than 2, I introduce two equilibrium values. My y2 is bigger than my y1. y1 is a sink, meaning the values approach it, and y2 is a source. On the other side, when I'm at the value a is equal to minus 2, similarly, I have a single equilibrium value that's a node, but my values are still increasing. Increasing on both sides. And as I continue to make a smaller, a is less than minus 2, again I introduce two equilibrium values, a y1 and a y2, and my behavior is the same. y1 is still a sink, so the values flow towards it, and y2 is a source, the values flow away from it. Looking at these phase lines, it's clear that the value minus 2 is a bifurcation value. Because to the left, here I have a single node, but the lines immediately to the right, as soon as I get slightly bigger than minus 2, I have no equilibrium values. And as soon as my values are just a little bit less than minus 2, I have two equilibrium values, and I have a sink and I have a source. Similarly, on the other side, the value of 2 is an equilibrium value, is a bifurcation value. These are both bifurcation values, because the behavior, when I move to the right, or to the left of the value 2, when I'm slightly bigger than 2, a is bigger than 2, I automatically will have two equilibrium values, a source and a sink. And when I'm immediately to the left, when a is just a little less than the value a equal to 2, I have no equilibrium values, and my function is always increasing. And so here are my phase lines, and here's my identification of my two bifurcation values in this problem. Okay, good luck.